Hello, I'm recording this video to help you understand the traffic light example source code that I've uploaded to ISIS, and also I shared on the WebEx Teams chat. Um, yeah, so let me show you how this works. So like as an example, I wanted to make the example as generic as possible. So like if you say like unzip the code in the source folder and like in a newly created folder called like traffic light example, you should not probably forget to add it as a net source folder. You have to tick it, and it knows that it has all the net files. Um, and if you look at the network that I've created, so I wanted to make it as generic as possible. There in the Spain's source traffic light example folder, you open the net file, and you'll see that there are like, say, like multiple rows crisscrossing each other. And here, just to let you know, if you see the distance between this traffic lights or this unit square is something like 800 meters, because I've searched somewhere that it's something like a desired distance between the traffic lights in the urban context, but feel free to modify it. And yeah, so on each like intersection, there are like, say, a traffic light, and you can see the traffic lights if you enter the traffic light mode. If you click them, you'll be able to see like what traffic program they're assigned. For example, this junction J1 is assigned a program 0, and say like there are different phases inside this traffic program. For 42 seconds, it's going to give green light to up and down direction. For 3 seconds, yellow light. For 42 seconds, it's going to give you green light to like in the horizontal direction, and then yellow light again. So it's going to be something like this. And for this example, I assume that the cars are coming from like outside. So they will be all generated on these like dead ends, and then we'll go just straight through the road and exit on the other side. They will not be making turns or anything. If you want to see how I've done that, you can take a look at the .ru.xml file and then see what I have done. So if you look at the default way, like how these traffic lights operate, you can launch Sumo GUI and open this traffic light example Sumo CFG. So this is a Sumo simulation without any, say, let's say, Vane's involvement, nothing smart. So I stop the simulation, give some delay, let it run, and focus on this junction on the upper left corner. The cars will begin to arrive soon. Yeah, the cars arriving. It lets all the cars from the left-right direction go through, and then let it wait. After 42 seconds, this has to wait. This goes through, something like that. This has to wait. So there is some wasted, like a waiting time. So I wanted to improve this. So what I've done here is that, if you make this traffic light and traffic programs from the net edit, it's going to be inside somewhere in the net file. So like if you scroll down in a very long XML file, which you can also read by, which can be read by human, you can see that for the traffic light J1, like program 0, which we have seen on the Sumo, net edit is just there. For 42 seconds, there's this state, which lets the vehicle go through up and down direction. For 42 seconds, the other way around, and then like the left-right direction, something like this. But instead of this, we want to use a different program than this timed traffic lights. So I created a separate file called TLS. You can take a deeper look. I mean, like the syntax is a bit like this, which is the same as the one given in the traffic light, this tutorial slides on the ISIS platform. And here, I mean, I've generated much simpler traffic programs. So for traffic light J1, I have a program called program ID, UD, like which lets the vehicle go through in the upright direction, and just one phase. And this phase will be manually controlled by our program. And the same goes for J10, J11, J2, J3, and whatsoever. If you go down a little bit, you will also find, like, say, program LR for J1, program LR for J10. As you can guess from the name, this traffic program lets the vehicle in the left-right direction to just go through and just has just one phase. So what I'm going to do here is that I'm going to say, like, use this program by including it in the Sumo simulation. We could do that by copying the name of the traffic light program like this with a comma, space, and now you're also using this traffic light program, which we have just seen. So but I mean, you don't need to modify. So like, because in the source code, I mean, this was already there. So I mean, if you just run the simulation, you'll only see the traffic light being controlled by the RSU example. But just in case, if you wanted to run the default traffic light from Sumo, you can just delete this and run this in Sumo GUI. Then you will see how the traffic light behaves, just like we have seen from like this video. And one thing I would like to show you is that I think we can just run or something. No, I mean, let's explain more thoroughly here. So there is a traffic light message. I mean, like, if you want to make an application making use of like this vehicular communication, you should think about like what sort of messages you would like to exchange. And I defined this like message, which extends the base wave short message. And I want to basically, like, say, send the information which is relevant for like doing traffic signal control. So for example, like the vehicles will send these messages. So I would like to know about the sender position, the vehicle's position. So how far, so we will know how far it is from the traffic light. And the sender speed, I mean, like, maybe you would like to do something about, say, like when the vehicle's like approaching, you would like to give the green light considering the approaching speed, so that, I mean, like, you'll have some estimations on the time that a vehicle reaches the traffic light. So like maybe speed is relevant. And also if you are considering like multi-lane road or anything, I mean, like, just a position with position and speed, it might be a bit difficult to figure out, like, say whether this vehicle is trying to make a left turn or right turn, I mean, which is not provided in this example. But I mean, there you might want to send also the lane information of the vehicle, on which lane it is. You can also do that. And of course, there's a timestamp and sender address, and that's pretty much it, what I want the vehicles to send. And I am guessing that, like, this is most the basic information you would also consider if you are considering a term project on traffic lights. You put out also something like it's an emergency vehicle or something like that, a Boolean variable stating whether or not it's an emergency vehicle, something like that. But feel free to add it. Yeah, so let me run and later explain the source code a little bit. So if I run this example here, so there are like 16 RSUs on 16 junctions. Is that? Yeah, let's see what happens. So if you look into the map, like if I scroll in, I have placed, like, say, the RSUs exactly on the junction. I paid some effort because, as stated in the traffic lights signal, like tutorial slides, I mean, the coordinates that Vanes uses and Sumo uses are slightly different. So on Sumo, I mean, this node was at, like, say, the coordinate something like Sumo coordinates start from the left bottom. So somewhere here is 0.0, and this one is 800.800, something like that. But the Vanes coordinates start from the top left. I don't know why this is the case. But I mean, like, what I've done here is something like I've manually designated all the, like, the XY coordinates of the traffic lights. So once I figure out the coordinate of one, like a traffic light, then I could just add like 800 to it so that I can easily calculate it. So there was some, like, a offset of 25 meters. And if I just have these, I mean, I found that it perfectly aligns to the traffic, like light positions here. So if I run this, you'll see that it's a bit slow because there are a lot of cars and a lot of messages being exchanged. So where are all the cars? So 36 seconds, the cars will begin to arrive here soon. Yep, the first car has arrived. It's going through and so on. But it's kind of hard to know, like, which direction is given the green light and red light. So yeah, it's kind of hard to know. So you see, there's no info. So one thing I have suggested is that, like, you could use some alternative command instead of, say, like in the when you launch when you execute this Vanes launch D stuff. At the end, you use sumo .exe. Instead of that, if you replace the sumo exe with sumo GUI exe, then the sumo GUI will launch, and you'll be able to see, like, how the traffic lights behave. So there are 3 vehicles waiting. There are 6 vehicles waiting. So in the middle, this traffic light switches, the phase switches, giving red light to that, and more vehicles waiting there. So, like, it's going to be 3. It behaves in a weird way. Real traffic light shouldn't work like this. But as soon as this leaves, this will... okay. Yeah, this red light's given. So as soon as less number of vehicles are, like, there, then here, then green lights will be given. So basically, it checks every 1 second. I mean, from which direction more vehicles are waiting, and then it gives green light to that direction. So basically, no cars will have to wait. But also, this has shortcomings in that, I mean, there's going to be very frequent traffic light signal changes. Maybe there's too many changes, which might result in less efficient traffic flow. But I mean, I didn't want to solve all the problems here. I just wanted to give you a working example. So you'll see this. How to achieve this is something you can, I mean, how to see this, how to see the simulation also on Sumo, not only on Vanes, is by doing this. So there is this command, just a sec. So usually you type this, right? This sort of thing before you launch. Otherwise, you'll see an error. So in the end, I mean, you type like sumo or sumo exe if you're from Windows. Instead of this, if you type GUI and run the simulation here, then, I mean, like instead of like Sumo default without GUI, I mean, like Sumo GUI will launch, which will also give you the green and red light visual information from the Sumo GUI. Yeah, that's a thing. And let me explain the source code a little bit. So in the Omnet INI, I mean, like we are executing the traffic light example, which is here. So which extends the scenario. We place like 16 RSUs on this map. That's what I have already shown you in the Omnet INI file. And then the traffic lights run TL RSU application, and then the vehicles run TL vehicle application. And first, if you look into the vehicle, which is a bit simpler, I mean, like it's the same stuff. I mean, like you initialize it, you say like use a C message to periodically reschedule something, WSM send event, and it does nothing until it subscribes to any, like, say, service. All the RSUs are broadcasting wave service announcements. And if the vehicles receive this wave service announcement and they are not subscribed to any other service, I mean, like they will subscribe to it, tune to the channel, service channel, find the service channel phase, calculate it, and then we will schedule an event at that time point in service channel. And like when this time comes, handle self message will be called, and you look at the type, what sort of like a message it was like typed in the schedule at. If it's this WSM send event, we already know that this is a traffic light message. We have we are trying to send. We are trying to send a traffic light message. You generate a new instance of traffic light. You fill in, they say, your ID, your like current position, current speed, like my ID is assigned at the beginning of the simulation. Current position is constantly automatically updated by this Vanes. The speed also automatically updated. But I think as Fan Tian has mentioned in the chat, this is only the speed. I mean, the position is always updated by Vanes, but the speed is only updated if you set this set host speed value to be true. So yeah, so anyway, it's going to be automatically updated if you only type that. So you'll send the speed value. You will also, like, say, stamp the current time using the sim time function. And a bit more tricky stuff is not tricky, but because I already provided you. So TraceI interface provides like a function to let you know which vehicle which lane this vehicle is on, and this is returns in string. You see a string class, but this one receives some sort of like a constant string. So we have to just convert it. But I mean, basically, if you print it on console, this just prints the name of the lane that you're standing on. Maybe if you want to make use of this info, you can also make use of it. You set the channel and you send it down to the MAC layer. And then the rest is handled by Vanes and Omnet, how it's going to be propagated over the air. And one thing is that here, I mean, like, this is advanced topic, so if you want to ignore it, you can just ignore it. But there's a pointer, and what this does is that it creates an instance of TL message on memory. It's gonna new operator returns a pointer, which will be saved here. So, like, what you're doing here is that you are duplicating it. You're sending a copy down to the MAC layer. And this copy will be deleted later from this whatever, like a software code, which is down there in the MAC layer. But I mean, this chunk of memory that you have allocated, I mean, like this would be still there unless you explicitly delete it. If you're interested in knowing more, I mean, like you can ask me questions about this, but like if you don't do this, it's going to be memory leak. You're generating a lot of messages. It's going to just accumulate without being deleted. And maybe for this simulation, it's going to be okay. But if this simulation runs for like many hours, I mean, you might encounter a situation that your program runs out of memory. If you encounter that, you can just let me know. But it's not a C++ course. You can just follow what I've done here and then just copy and paste and use it. So you find the service time slot in the service channel phase. You schedule a new one, and then like you end the function. Because you have scheduled a new one, when this time comes, this will be called again, and so on. For other kind of messages that we haven't defined, I mean, we still want some like the function from the inherited class to run. So like there is also an if-else clause. So to the core of the traffic light, this logic. Here, I mean, like due to the reasons I mentioned in the slide, I mean, we have defined like not only the traffic control event. So I mean, I want basically the traffic light to wake up every 1 second, check the number, and set the traffic program. And then that event will be called traffic control event. And then I want to define another event, which will be only called once at the beginning of the simulation. But for some reason, this has to be done. This is weird. I mean, like there are 2 events, and like this TLRSU, the software will run on all of the traffic lights. But we would have to somehow like let this software code to be aware of which traffic light it's controlling. So I've written a very stupid piece of code which will run at the initialize. So it's gonna store the traffic light ID based on like my ID, so the network ID of the RSUs. So I have noticed that when you run this vein simulation, place 16 RSUs, the my IDs of the RSUs, the first one on the top left corner will be 25. The second one, like on the like first row, second column will be 30, 35, 40, and so on. So basically, I can exploit this prior knowledge in the source code to assign like the traffic light RSU applications, RSUs, to each of the traffic lights. So the first RSU is assigned traffic light junction 1, junction 2, junction 3. So from the top left to the bottom right. Yeah. There are 16. So, I mean, if you start from 25 and then there's a 5, this interleave, then, I mean, like it's going to end at 100. If we have a my ID of the RSUs other than this is an error. So I crashed the program. Yeah. And what it basically does is that at the beginning, it only scheduled this one init message. And when like this event is called only at the very beginning at simulation time 0.0, what we are doing is that we are trying to get access to this trace-i interface to Sumo. For some reason, this cannot be done in initialize. This this pointer is only available after the simulation starts. So I set this, but don't forget, forget about it. You can just copy and paste and use this code, and then change only the parts which are relevant for your term project. This has to be anywhere there. Just copy and paste, and you can use it. So here, what I do here is that basically this is the traffic light control logic. This is the only part you will have to modify. If you want to implement your custom traffic, maybe not the only part, you will have to understand and modify some other parts. But I mean, this is the core of the traffic light control algorithm. You count the number of cars from the left, number of cars from the right. You sum it up. You count the number of cars from up and number of cars from down, and then you sum it up and see which one is larger. If there is a more number of cars from up and down, you set the program to be up and down. So this is the part where you tell the Sumo program to change the traffic light signal program. And otherwise, you give priority to LR. It's as simple as that. This if clause is just for debugging. If you comment it out, it's still going to work fine. But I mean, to just make sure to give you some info, so you can enter any traffic light RSU my ID and see like how many cars are waiting from the left, right, up and down direction here, something like that. And one more thing. So I mean, like we are counting the number of cars from left, right, up and down direction, and then this has to be somehow, say, like maintained. So how I do it is that upon receiving on WSM from the RSU side, when RSU receives a message, I mean, it checks from like how far this message has come from and from which direction the sender is. We maintain this data structure, which is left, right, up, and down. So first, like it parses the message. So it checks if it is the wave short message I received is the traffic light message. If it is, it's going to enter this if clause. I parse the sender message, get sender address from the packet that has been just received. Sender position and sender speed, I get it. Also the lane ID, I get it. If you print the lane ID here, you can see the name of the lane ID, which is also the same as the one you can check from the Sumo NetEdit and the information. So I calculate the distance. I mean, you do a minus of the vector. So the distance, you'll have to take the length, norm of the vector. So you take the length and store it in this double variable. And I want to look into the relative position, which is also a vector, relative speed, which is also a vector. I mean, you don't have to have relative speed because the speed of the RSU will be always 0. It doesn't move. But I mean, just like to be consistent, I define these two variables. If the distance is farther away than 200 meters, I mean, like it's too far, you don't have to consider it. You don't do anything. If it's within 200 meters, we want to start processing. So what I do is that you take an inner product of the two, say, like vectors, relative position and speed. And if it's less than 0, this means that, I mean, if you think about an RSU and then a vehicle and draw the two vectors, this relative position and the speed is traveling. So if it's minus, then it means that the vehicle is getting closer to you. I mean, it's a simple math. I wouldn't explain it. So it's smaller. Then what I do is that you take an absolute value of the relative position in the x direction and then the y direction, and you look at what is more significant. So like I'm basically trying to see whether it's coming from left or right or up and down. So you look at if it's a relative position in the x direction, so it's coming from either from the left or the right, then what you do is that you look at the relative position. If it's on the left, you check and add left. You call this function. And what this does is that it checks the sender ID and then sees if the sender ID is already in this the data structure left, and it adds to it. If it's already there, it doesn't add, and it just updates the relative position and speed. If it's from the right, I mean, you call the check and add right. If it's from the north, north is a bit tricky because I mean, like this Vane's coordinates. I mean, the origin is the upper right, upper left, so it's a bit confusing. But I mean, if it's smaller than 0, it's coming from up from the map we visually see. So you call this and you call that. And if it's not getting closer to the traffic light, I mean, traffic light don't have to care about it. So you remove it from the whatever vector it was, and you call this function. Yeah, that's basically about it. So like whenever you receive this on WSM, you update the left, right, up, and down, and yeah, and then like this algorithm is called every 1 second, and you control the traffic light. This program is as simple as that. Maybe a small remark on these functions: check and add left and right. Yeah, here, like it's just defined down there. So what it does is that, so this left, these are the vectors of like a vector containing car data. Car data is just up there. So this is a data structure you want to maintain from the RSU. You can also modify it as you want. Maybe if you want to use the lane info, you can add lane info just down there, something like that as well. But I mean, like in here, I don't do it. You can later use it if you want. But it basically stores my ID to identify like which vehicle. So if one vehicle is sending a lot of messages and you don't store the ID, I mean, you cannot identify it so that you cannot say count the number of vehicles on there. So you should keep track of like which vehicle is sending the messages. So my ID, position, and speed. And this, like we define a new data type, like just like int, but I mean like a car data, which contains these 3 values. And we define a vector of these metadata from cars, 4 of them from left, right, up, and down. Like this standard vector, it's something like basically provided by C++. So if you Google it, you'll find out all the functionalities you can use about it and a lot of example codes. But you don't have to go through all of that. So basically what you can do here is that if you call like, this is a vector. If you call I, you are accessing the ith element of this vector. And in this ith element, there's metadata. You call like point my ID, then you'll access this, I don't know, this ID, yeah, my ID of the ith metadata stored in the left direction. So basically check and add left, what it does is something like you go through the vector and see whether this sender ID is already in the left vector, meaning that it has already sent some data from the left direction, and then it's going to send every 1 second. It's going to, of course, send multiple messages as it approaches the traffic light. So, I mean, like if it overlaps, you don't add a new element, but you just update the position and speed. So if you go through all the for loop, and if you don't enter this if clause, this means that, oh, this is a new vehicle approaching. And you can see you can know it by using this Boolean variable. If it's not a known car, what you do is that you add it to the vector. And then you can call this pushback function. I mean, just Google it. There's plenty of examples. And you generate a new car data and then, yeah, put it there. So it's basically, you do the same thing for the right, up, and down, and you maintain the data structure. And actually, these functions, I don't use it. I can delete it, sorry. But I only use this remove from vector. What it does is that it's just going to go through the left, right, up, and down, and look for this vehicle. And if you find the ID, you just erase it from the vector so that your program is up to date. So what I'm trying to do here is that just run it and show you how it works. And I run it. Because I entered Sumo GUI, this will be there. A program starts running. And it's fairly slow. I'm sorry. Yeah, it's a large thing. If you look here, there's some debug info I'm printing from the first traffic light at the upper right, upper left. LRUD, so there are no vehicles nearby. It's printed every 1 second. Oh, so it's going to take a lot of time. Yeah, let's see, 47 seconds. Yeah, so vehicles coming. So you can see that the vehicles coming from the left are increasing, and there are vehicles coming from the up direction. It's increasing. So based on this info, it's going to give green light. So likely it's giving green light to the upper stuff. And it's equal. When it's equal, it's going to give it to the left, right. It's going to be again up. Let's see. Let me check. Can we already see it? Yeah, you can see the green light is given there in the up down direction, and you can see how this works. Basically, that's it. Yeah. So let me kill this and end this video, not to make it too long. And I hope this video helps you understand the source code. If you have any questions, just ask it on the chat or send me email or whatsoever, and I'll be more than happy to help you. And I can help you even programming. So like, just reach out to me. Hello, I'm recording.